Welcome to AI Paper Podcasts. We're the place you come to for deep dives into the really impactful new research in AI and tech.
That's right. And today we've got a big one, a really significant survey paper.
Yeah, absolutely. It's titled A Survey of Self-Evolving Agents on Path to Artificial Superintelligence. This comes from Huanan Gao and a whole team, researchers from places like Princeton, Tsinghua, a lot of heavy hitters.
It really maps out this fascinating progression, doesn't it? Moving from the kind of static large language models, the LLMs we mostly talk about.
Right, the ones that are trained and then that's it, they're fixed.
Exactly. Moving from those to what they call truly self-evolving agents. It's sketching out a possible path, towards artificial superintelligence, ASI.
And the core idea, just to summarize for everyone, especially if you're catching the short version of this, it's about systems that don't just stop learning after training. They continually learn, adapt, improve themselves, like in real time.
Yeah, the AI literally gets smarter on its own. It's evolving its models, its context, the tools it uses, even its own fundamental architecture.
It's a huge shift, isn't it? Not just bigger models, but models that learn how to teach themselves, adapt, grow, almost like we do.
Precisely. From an AI that just knows things to one that actively learns to know more. That's the leap.
Okay, so let's unpack this properly.
Yeah.
The paper starts with a really fundamental question. What did these agents actually evolve? And they break it down. 4 core pillars. Let's start with the first one, models. What exactly does that mean in this context?
So evolving models. This gets right to the agent's core thinking, its cognitive processes. Think of it as the agent's brain.
Okay.
It's not just running a fixed program. It's about systems that can actually learn to refine their own internal policies or adapt lessons from their experiences.
Like learning from mistakes or successes.
Exactly. Think of an athlete, maybe, refining their technique with every single practice session. The paper mentions systems like SEA or raised in these show models, learning to self-improve their decision-making over time. They're constantly tweaking their approach based on what works.
Wow, so the AI is actively changing how it thinks. That's, profound. Okay, pillar number 2 in the paper is context. This was interesting because it lets the agent change its behavior without necessarily changing that core model, right?
That's the idea. And within context, they first highlight memory evolution.
Memory. How does an AI's memory evolve?
Well, it's critical. It's about how agents manage their information. Storing things, sure, but also deciding what to forget and how to retrieve the relevant bits efficiently.
So not just a giant database.
Not at all. They mentioned SAGE, for instance, which uses ideas like the Ebbinghaus forgetting curve. Basically, it intelligently prioritizes information, deciding what's likely important to keep and what can be discarded, like how we don't remember every single thing we saw yesterday.
Right, makes sense.
And then you have things like Men0, which goes even further. It can actively add new facts it learns, merge similar information, update things, and even spot and delete contradictions in its long-term memory.
So it's actively curating its knowledge.
Precisely. It's not just passive storage. It's maintaining a coherent, useful knowledge base. They also mention Expel, which processes past experiences like task attempts to generate general insights or rules, turning one-off experiences into long-term know-how.
Okay, so optimizing memory is one part of context. The other part they mention is prompt optimization. This sounds more like tweaking the instructions we give the AI.
Yeah, exactly. It's about refining the instructions, the prompts that you feed into the LLM backend. This can directly change its behavior, often without even touching the underlying model weights.
Clever, like getting more out of the engine you already have.
Totally. Methods like APE, for example, automatically generate and test prompts to find the best ones for a task. Prompt Breeder uses evolutionary algorithm survival of the fittest for prompts, essentially.
Oh, okay.
And what's really cool is how this applies even to complex workflows where maybe you have multiple calls to the LLM. Systems like DSPy, Trace, TextGrad, they treat prompts almost like differentiable parameters, meaning you can optimize them using techniques similar to how you'd fine-tune a neural network's weights. You get structured feedback and adjust the prompts accordingly. And this isn't just for single agents. Evo Agent and Agent Square are applying this to optimize prompts for whole teams of agents.
That is powerful, making the instructions smarter. Okay, moving beyond these internal changes, the paper talks about tools. This feels like a big step, the shift from agents just using tools we give them to agents actually making their own tools. How big a deal is that?
Oh, it's a massive deal. Monumental, really. Autonomous tool discovery and creation means the agent isn't stuck with a fixed toolkit anymore.
It can build what it needs.
Exactly. If it encounters a problem and realizes it lacks the right tool, it can try to build it. Voyager is a great example they cite in Minecraft. It explores, tries things, fails, learns, and actually builds up a library of skills. It teaches itself how to craft, mine, navigate things it couldn't do before. And others, like Alita and ATLAS, can search code repositories or even write new code, new functions when they hit a capability gap. Creator tries to formalize this. Skill Weaver synthesizes new skills into usable APIs.
So the AI is essentially programming itself new abilities.
In a way, yes, which is incredibly powerful, but, it also brings up important safety considerations about letting AI generate and run code freely.
Definitely something to keep an eye on.
Yeah.
And just creating a tool isn't enough, right? They need to get good at using it, or maybe the tool itself needs work. The paper talks about mastery through iterative refinement.
Yeah, exactly. A newly created tool, especially one an AI just whipped up, might be, buggy or brittle. It might not work perfectly the first time.
Sure.
So frameworks like LearnAct and Duraft allow the agent to self-correct. It analyzes feedback, maybe compiler errors if it wrote code, or weird results from an API call, and uses that feedback to debug and improve the tool, not just the code, but maybe even the description of how to use the tool.
So it iterates, refines.
Right, turns a potentially flaky new skill into something reliable. It's about honing those capabilities.
Okay, that covers models, context, tools. The final pillar is architecture. This is about the agent's internal logic, how it's put together, and even how teams of agents work together. Let's start with single agent system optimization.
Right, so this is optimizing the structure of one agent. TextGrad, for instance, uses something called textual gradients. It lets the agent analyze its own internal workflow, like the steps it takes to solve a problem, and figure out which parts could be improved.
Analyzing its own thought process.
Sort of, yeah. Agent Square focuses on finding the best modular design, breaking the agent down into efficient components. But then you get into the really radical stuff, like Darwin Gödel Machine and AlphaVolve.
What do they do?
These systems allow the agent to directly modify its own source code.
Wait, really? It rewrites its own programming?
That's the idea, making its fundamental structure learnable, adaptable.
Yeah.
It's kind of mind-bending. A glimpse into AI that can truly revise itself at a fundamental level.
That is mind-bending. Wow. And it's not just single agents. They also cover multi-agent system optimization, how teams of AIs work together.
Exactly. How do you orchestrate collective intelligence effectively? Systems like ADS and AFlow treat this as an optimization problem. They automatically search for and discover workflows for agent teams that can actually outperform designs humans came up with.
So finding the best way for them to collaborate.
Right. ScoreFlow trains models to generate good team structures or topologies. RIMA uses multi-agent reinforcement learning, so the agents learn collaborative policies together. The key idea is that the organization itself can evolve, leading to emergent group capabilities.
Okay, so we've got models, context, tools, architecture. The next big question in the paper is, when does this evolution actually happen? They identified two main timings, inter-test time and inter-test time. Let's start with inter-test time. What's that?
Intra-test time self-evolution is about adapting during a task, in real time. The agent is trying to solve something, realizes it's struggling or could do better, and initiates learning right then and there to improve for that specific instance.
So learning on the job immediately.
Pretty much. It's about reacting and improving on the fly.
Okay, and how does in-context learning, ICL, fit in here?
Well, during the task, an agent using ICL might use self-reflection. It could generate critiques of its own plan, revise its strategy dynamically based on feedback it's getting from the environment, all within the context of that single task. Reflection and AdaPlanner are examples here. They adapt their plan mid-task without actually changing their core programming, just by thinking differently in the moment.
Like thinking aloud and correcting course. What about supervised fine-tuning, SFT, at test time? That sounds like it makes more permanent changes.
It generally does. Here, the model might perform immediate self-edits. It could restructure how it's representing information, or maybe even invoke some tool to calculate gradients and actually update its own weights. It's a persistent change, even if it happens right there during the task. Self-adaptive language modeling fits here. The model teaches itself how to adapt now and remembers that adaptation.
And reinforcement learning, RL, can happen in real time too.
Absolutely. An agent might develop a new capability it needs right then.
Right.
LDR is an example they give. It uses test time RL. If it hits a really hard problem, it can generate variations of that problem and do some intense focused learning right there to figure out how to crack it, acquiring a skill just in time.
Very responsive. Okay, that's adapting during the task. What about the other mode, inter-test time self-evolution? This happens between tasks.
Right. This is about learning from accumulated experience over time between task completions. It's more retrospective, leveraging a history of interactions to improve future performance more broadly.
So, reflecting after the fact to get better next time, how does ICL work here?
In this mode, ICL uses past results, feedback from previous tasks, as context for new problems. So methods like ICRL maintain histories of observations, actions, outcomes in the agent's context window. The agent gets better over, say, days or weeks as it sees more examples, not just within one 5-minute task.
And SFT between tasks. How does that differ from the real-time version?
Inter-test time SFT is more about iterative self-improvement cycles, often involving generating synthetic data. Systems like Self and Star are good examples. They might evaluate their own outputs, figure out how to improve them, and use those improved outputs as new training data to fine-tune themselves, bootstrapping their own improvement offline.
Creating their own better training data. Clever.
Yeah.
And finally, RL in this inter-test time context.
This usually involves more extensive interaction with an environment, often simulated and maybe sophisticated curriculum design. Ragen and WebRL work like this, continuously refining their policies through potentially millions of trials in a simulated world. It's about deep, systematic learning to build robust skills that generalize, which often takes too much time or data to do effectively during a single task.
Right, building up that core competency over the long haul. Okay, so we have the what and the when. Now for the how do these agents actually do the evolving? The paper maps out families of methods, starting with reward-based self-evolution.
Yeah, reward-based methods are fundamental. It's all about designing reward signals feedback to guide that self-improvement loop. And this comes in several flavors.
Okay, like what?
Well, first there's textual feedback. Using natural language, it's detailed, interpretable. Reflection and Ada Planner use this. They might get verbal critiques, maybe generated by another part of the system or even the agent itself, and use that to revise their plans. It's like the agent reasoning through feedback.
Makes sense. What about internal rewards?
Internal rewards leverage the model's own state, like its confidence level or probability estimates. Systems like CISC and self-rewarding language models allow the model to basically evaluate itself based on how confident it is in its answer. This reduces the need for constant human labels, which is great for scaling up.
Letting the AI judge itself? And then there are external rewards. More straightforward.
Generally, yeah. Derived from outside sources, the environment, maybe getting feedback from a tool it used, majority voting if you have multiple agents trying something, or explicit rules. SWDev and Sika learn this way, interacting with real tools and systems and getting direct feedback on whether they succeeded or failed. Crucial for real-world interaction.
Got it. And the last one sounds intriguing. Implicit rewards.
This is fascinating. It turns out LLMs can often learn from feedback that isn't explicitly marked as a reward. Research like reward is enough shows they can do in-context RL just from scalar signals, numbers basically, embedded in the text. And endogenous reward even suggests LLMs might inherently encode reward-like signals just from their standard training.
So they can pick up on subtle cues about performance.
It seems so. They don't always need a big, flashing, good job or bad job signal.
Okay, that's a good overview of reward-based methods. Next, the paper discusses imitation and demonstration learning, learning from examples.
Right, learning by watching, essentially. Very powerful when you have good examples. One type is self-generated demonstration learning. Here, the agent actually creates its own training examples through refinement.
How does that work?
Star is a key example. It tries to reason through a problem, maybe gets it partially right, then refines its reasoning steps. V-star adds a verifier to check the quality. Essentially, the agent bootstraps its own skills by generating and learning from its own improving attempts, becoming its own teacher.
That's cool. And they can learn from each other, too. Cross-agent demonstration learning.
Yep. Sirius, for instance, allows agents in a multi-agent system to share their experiences, their successful task executions. They build a shared library, learn from the collective successes, like a team sharing best practices.
And there's also hybrid demonstration learning, mixing both.
Exactly. Combining self-generated examples with external ones, maybe from humans or other agents. RISE uses structured self-reflection to generate corrective demonstrations after failures, blending its own internal debugging with external guidance. Makes for robust learning.
Okay, The final major category for how is population-based and evolutionary methods. This sounds like it's taking inspiration directly from biology.
It absolutely is, like digital natural selection. Instead of just optimizing one agent, you maintain a whole population of agent variations simultaneously. This allows for a broader search for solutions and can discover really novel approaches.
So survival of the fittest AI.
Pretty much. For single-agent evolution, you have things like the Darwin-Gödel machine, evolving agents that literally rewrite their own Python code, selected based on performance. Genome uses genetic algorithms on model parameters. Spin uses self-play agents compete against past versions of themselves, driving improvement through competition.
And this applies to teams too, multi-agent evolution.
Yes. EvoMac optimizes the composition of an agent team, kind of like training a neural network. Puppeteer evolves a central orchestrator agent that learns to select which specialist agents to activate for a given task, fostering coordination. It's about evolving the team structure and collaboration strategy itself.
That's a whole other level of optimization. The paper also mentions some cross-cutting evolutionary dimensions like online, offline, on-policy, off-policy, reward granularity.
Yeah.
These have more nuance, right?
Definitely. They're about the specifics of how these methods are deployed. Online versus offline is about learning during live interaction versus learning from a collected batch of data afterwards.
Okay.
Trade-offs in speed versus stability.
Okay.
On-policy versus off-policy learning. That's about whether the agent learns from experiences generated by its current strategy or strategy from the past or even other agents. Off-policy can be more data efficient, but sometimes harder to get right.
And reward granularity, how detailed the feedback is.
Exactly. Is it just a final pass-fail for the whole task? That's coarse. Or does it get feedback on every single step? That's fine-grained. Or something in between. The level of detail impacts how effectively the agent can pinpoint what needs improvement.
Right, lots of design choices there. So we've got the what, when, and how. Let's talk about the where. Where are these self-evolving agents actually being used or making an impact? The paper splits this into general domain and specialized domain.
Right. General domain is about broad, versatile assistance. Think digital helpers. Here, a lot of the evolution focuses on things like improving memory over time. Mobile Agent E and Mobile Steward are examples they give for improving performance on complex smartphone tasks by remembering past interactions.
Getting better at everyday digital tasks. And curriculum-driven training it fits here too.
Yes, helping agents build broad competence. WebRL uses a self-evolving curriculum for web navigation. If the agent fails, the system generates slightly easier related tasks to help it learn that skill progressively. Voyager in Minecraft does something similar, building up its skills from simple to complex through an automatic curriculum.
Okay. Then there's specialized domain evolution, where agents are really focused on getting good at narrower tasks. What are some key areas?
Coding is a big one. Sika is an agent that literally edits its own code based on compiler feedback or test results. EvoMac and Agent Coder focus on optimizing multi-agent teams for code generation, making them much more efficient and producing better code through iteration. AI is becoming better programmers by learning from errors.
Makes sense. What about interacting with software, like graphical user interfaces, GUIs?
Yeah, GUI agents are evolving too. Navi learns from its mistakes to get better at completing tasks in Windows. Web Voyager uses self-fine-tuning to improve its success rate on websites it hasn't seen before. Auto GUI learns by mining annotations about how GUI elements work. They're getting better at seeing and clicking, essentially.
The financial sector seems like a prime candidate too.
Definitely. Constant need for adaptation there. Quant Agent refines its predictions and knowledge using feedback from simulations and real trading, improving its accuracy. Trading agents use reflection and RL to constantly tweak their strategies for volatile markets.
And education, how are they being used there?
Two sides, really. For learners, personalized tutors like PACE can adjust their teaching style, the prompts they use, based on the student's profile and how the conversation is going. For instructors, systems like IVIP use teams of LLM agents that critique each other's explanations in real time to generate better educational content.
Wow. Adapting to both the student and improving the teaching material itself, that's pretty sophisticated. Okay, so these agents are being applied in some really interesting ways. But how do we know if they're actually good? How do we evaluate them, especially since they're constantly changing? The paper proposes a framework with 5 core dimensions. Why is a new framework needed?
It's absolutely crucial because, like you said, they change. Static benchmarks, just testing them once, don't capture the whole picture. The first dimension they propose is adaptivity.
Measuring if they actually get better.
Exactly. Can they improve performance on tasks within their domain as they gain experience? Metrics look at things like success rate by iteration steps or adaptation speed. It's about quantifying that learning curve.
Okay, then retention. This sounds like it tackles that catastrophic forgetting problem.
Precisely. Does the agent remember what it learned before, or does learning new things make it forget old things? Metrics like forgetting measure accuracy drops on old tasks, while backward transfer measures if learning new stuff actually helps performance on old tasks. Positive backward transfer is a big win.
Right, you want to build knowledge, not just replace it. What about using that knowledge on totally new things? That's generalization.
Yes. Can the agent apply what it's learned to new domains or tasks it hasn't explicitly trained on? You'd measure this with aggregate performance across diverse test suites, or specifically performance on out-of-domain tasks. Super important for real-world usefulness.
And practicalities matter too. Efficiency.
For sure. How much does it cost to run this evolution? How fast is it? Key things are token consumption, basically computational cost, time expenditure, number of steps to improve, maybe tool productivity if it's making tools. Is the evolution process itself efficient?
And the big one, safety. Given they modify themselves, this seems paramount.
It's hugely important, maybe one of the biggest challenges. Does the agent develop unsafe, biased, or just undesirable behaviors as it evolves? Metrics try to capture this. Safety score, harm score, risk ratio, refusal rate for inappropriate requests, leakage rate for private info. Ensuring they stay aligned and safe as they change is critical.
Yeah, that sounds incredibly challenging, but necessary. The paper also outlines different evaluation paradigms, how they actually test these things.
You're right. They mention 3 levels. Static assessment is the traditional snapshot test once on a benchmark like SWE bench or agent bench.
Okay, the baseline.
Then short horizon adaptive assessment. This looks at improvement over a shorter period, maybe within a single session or across a few interactions. You track that adaptivity curve.
Seeing if it learns quickly in the moment.
And finally, the really important one for these systems, long horizon, lifelong learning ability assessment. This is about evaluating continuous learning, retention, and knowledge transfer over extended periods across diverse tasks. Benchmarks like LTM benchmark and lifelong agent bench are starting to emerge here. It's about assessing if the AI can truly learn and grow over its entire life.
That sounds like the ultimate test for these evolving agents. So looking ahead, what are the big open challenges? The paper highlights a few key future directions. One is personalized AI agents.
Yeah, getting agents to really understand and adapt to individual users. Challenges here include the cold start problem. How does it personalize when it knows nothing about you yet?
Yeah.
Managing long-term memory specifically for personalization and making sure it aligns with your facts and preferences without just reinforcing biases. Needs new kinds of evaluation too, since everyone's different.
Right. Then there's generalization, that classic AI challenge.
Still a huge hurdle. How do you design architectures that can scale and adapt across different domains without constant, expensive retraining? How do you really solve catastrophic forgetting in continual learning? How do you make knowledge easily transferable between agents? It's that tension between being a specialist and a generalist.
And safe and controllable agents comes up again as a major future direction.
Absolutely. Dealing with risks like users giving vague instructions that lead to bad outcomes or the agent being exposed to harmful stuff online. Future work needs better ways to identify sensitive information, manage agents if their goals conflict with ethical constraints, and gather diverse real-world data to train safer behaviors. Building reliable guardrails for systems that rewrite themselves is key.
And finally, they talk about ecosystems of multi-agents, moving beyond single agents.
This feels like the next frontier. How do you balance individual agent reasoning with collective goals? How do you create efficient ways for them to collaborate dynamically? And how do you evaluate these evolving teams where roles might constantly shift? It's about orchestrating complex, adaptive AI societies, essentially.
Wow. Well, this has been a fascinating dive into self-evolving agents. It really paints a picture of AI moving towards something much more dynamic, much more alive in a sense. Not just static tools, but systems that learn, adapt, and grow continuously.
It's a complex path for sure, full of challenges, especially around safety, generalization, and just making the evolution efficient. But the progress is undeniable.
Absolutely. We're seeing steps towards AI that can genuinely enhance its own intelligence and adapt to our constantly changing world. So thinking about all this, what really stands out to you as the most revolutionary piece? And maybe for you listening, what questions does this raise about the future of AI and the areas you work on or follow? Something to think about.